So, we derived an expression for the eccentricity for central orbit, especially for inverse square force law. Now, we want to derive an expression for the velocity. Now, again we start with this equation, which is du d theta square plus u square equal to 2 m by L square E minus V. Recall that E minus V is nothing but the kinetic energy T, which we can write as half m V square, V being the speed at the orbit at any point. So, once we do this substitution, we get a relation, 2 cancels out, we get a relation that V square is equal to L square by m square du d theta whole square plus u square. Now, so this is a general expression for any velocity for any central orbit. Now, we want to see what is the specific form for a conic section. That means, if we consider the inverse square force field, then we know that u equal to 1 by L 1 plus epsilon cos theta. Once again we are setting theta 0 equal to 0. So, that means, our reference line is already at 0. Now, once we do that, we see if we substitute this into the equation, once again we have to evaluate du d theta, and then we have to perform this summation of du d theta square plus u square, and we will see that it will reduce to I will just give you the final form, because a similar calculation we just very recently did. So, I will just give you the final form of this. It will be epsilon square by L square plus 2 epsilon by L square cos theta plus 1 by L square. So, this is the general expression for velocity in an inverse square force field. That means, when the path of the particle is a conic section, could be a circle, could be a parabola, could be a hyperbola, could be an ellipse. This is the general expression. Now, for specific cases, we have to substitute specific values of epsilon. We know that epsilon has different ranges. We will see that in little more details very soon. Okay. Now, let us focus on the problem set. Problem number 7 is what we are trying to attend now. The attractive inverse square force field F r is minus k by r square. Show that the speed at any point of the path may be given by v square equal to k by m 2 r minus 1 by a for an elliptical orbit, and another expression given for a parabolic orbit. So, what we need to do is we need to introduce we need to start from this particular expression, and for the first part we have to use some properties of the elliptical orbit in order to get the expression which is given in the problem set, and for the second part we can use the separate set of parameters for the separate set of modification to this particular relation in order to get it for parabolic orbit. So, we will start with the second one because this is slightly more trivial. So, what happens in a parabolic orbit? So, we are doing the part 2 first. So, what happens in a parabolic orbit? We have epsilon equal to 1. Just a minute. I think this is better, right? Epsilon equal to 1. Now, if we put epsilon equal to 1 into this expression, then we see that v square is equal to L square by m square. So, see it will, if you put 1 here, these two expression will look alike, similar, and so it will add up to give you 2 by L square. There is a 2 here. So, that 2 will come out, and you see it reduces to 1 by L square plus cos theta by L square. Also L square can be taken out and we can write it as 2 capital L square by m square small l square 1 plus cos theta. Now, it is time to substitute for small l. You remember this expression for small l is, I always forget this expression. So, it will be, it will be L square by m k, capital L square by m k. If you do the substitution here, then we see that it will be capital L to the power 4 m square k square, right. So, it will be capital L to the power 4, you have m square, you have k square, m square goes, you have 1 L square left, and without surprise you get the expression which is given in the problem set as 2 k square by capital L square into 1 plus cos theta. It is exactly the expression which is given in the problem set. Is it so? Yeah, right. So, it is fine. So, we are good here. Now, if you look at it carefully, so we can now if you try to I mean using this relation, if you try to see how does the speed vary along the orbit of a parabola. Okay. If the equation is L by R equal to 1 plus epsilon cos theta, then I have discussed already, then this will be your focus, right, and your parabola will be something like this, right. So, this is your, for any point, this is your R and this is your theta, or for any point here, this is your R and this is your theta, things like that. So, if you put theta equal to 0, that will correspond to this particular point, and if you put theta equal to 180 degree, that means you have to extend the radial vector to a point which is essentially at infinity. As the particle or as the object moves away from the force center, if it moves away from the force center, your theta becomes more and more, and in the limiting case when r goes to infinity, your theta goes to 180 degree. Now, if you put theta equal to 180 degree, you will get a velocity equal to 0, right. And if you put theta equal to 0, you get a velocity v, or v corresponding to theta equal to 0, which is given by, it will be 2 into 2 4 k square by L square, v square equal to 4 k square by L square. So, v will be equal to 2 k by L, 2 k by L. Of course, I am omitting the negative sign because speed cannot be negative, velocity can be. So, this is at v equal to v at theta equal to 0 and v at theta equal to pi, which is a point at infinity. If you put it in here, it will be 1 minus 1 equal to 0, right. So, these 2 points, which one is here and the other one is at infinity, these are called the epicidal points for an orbit. We will come back to that in a moment, but for now let us focus on the first part. So, we did the second part, we have to now go back and do it for a elliptical orbit, right. Same velocity expression, same everything for elliptical orbit. Now, we have to for elliptical orbit, what we have to do is we need to rearrange this equation a bit, and we can write it as v square is equal to, okay, I will just use the space here, won't write the same thing don't have to write the same thing again, I can just use the space here. What we can do is, we can put a 2 here, right. If we take, yeah, so I can put, just give me a second. Sorry, not here. We can put a 2 here, and it is just a mathematical manipulation, and we can write it like this. Right. Now, this is equal to, now if you take these two terms separately and take these two terms in another group, in the from the first group, you get L square by m square two by L square into 1 plus epsilon cos theta. So, it is 2 by L square into 1 plus epsilon cos theta, and from the second group it is plus 1 by L square epsilon square minus 1, right. So, we are doing it for, and now remember that we are doing this calculation for elliptical orbit. Now, what happens for an elliptical orbit is, we can, if you recall, for an elliptical orbit, A, the length of the semi major axis is given by L by 1 minus epsilon square, right. Now, from the first bracket inside, recall that L by r is equal to 1 plus epsilon cos theta. So, 1 plus epsilon, we can substitute L by r for 1 plus epsilon cos theta, right. So, if we do that, we get, or we can just, yeah, L by r, and for the second one we can use this relation to substitute. Okay, for now we just keep it like this, and we have, so 1 minus epsilon square is L by a. Okay. So, we can just put L by a. Okay. Now, it looks better. Now, if you simplify this, I think we are almost done. See, L, 1 L cancels here, 1 L cancels here, leaving behind 2 by r minus 1 by a. So, V square is equal to this for an elliptical orbit, right. So, we are, once again we got an expression of velocity, which in terms of angular momentum m, length of semi major axis, m being the mass, length of semi major axis, and the radial displacement at any point on the elliptical orbit. Now, this result has a slightly more, slightly higher, slightly more significant things hidden inside. If you just do one more mathematical step and write this as 2 L square by m square 1 by r minus 1 by 2 a, right. Now, so V square is equal to this. It is the same expression, we just wrote it in a slightly different manner. Although the same from the first expression also, it's not very different. Now, put r equal to 2 a in any of the expression, either this or that, you will immediately see that the velocity goes to 0. Okay. But in principle, r can never be 2 a. Why? Because in an elliptical orbit, how does the orbit look? This is my elliptical orbit, this is my origin, let us say. So, this is first focus, this is the second focus. So, this is minimum and maximum length of r. So, this length is r min, this length is r max, this length from here to here is 2a. Okay. So, maximum of r is r max, which if you go by the equation is given by L by, the equation once again is L by r equals 1 plus epsilon cos theta. So, maximum of r is reachable if you put theta equal to, so please remember for any displacement this is your r, this is your theta. So, if you put theta equal to 180 degree, you get the maximum value for r. So, r max is L by 1 minus epsilon, r min is L by 1 plus epsilon. And if you recall, a and r, they are related by a and L, they are related by a equal to L 1 minus epsilon square. Okay. So, r can never be L, r can never be a. So, what is the significance of this 2a here? Significance is at r equal to, we can consider this as a situation as if we draw a circle with the center at this particular focus and with a radius of 2a. So, 2a will be here, the same 2a will be somewhere here. So, it will be a big circle. So, same 2a, yeah. So, it will be something like, I do not know how good this circle is, I hope it is good, okay. And it will be, you have to finish it, I mean close the thing. Now, think of it this way, when your mass point is here on this big circle, let us say this is stationary here, you allow it to drop, if you allow it to drop from this height, there is a force center here. So, it will be attracted towards this force center. By the time it reaches this position, which is the location of this particular, which is a valid location on the orbit, it will attain a velocity v square or velocity v, which is given by this particular relation. So, the velocity at any point on this elliptical orbit is the same velocity of mass point will achieve if it is being dropped from any point on this big circle and ends up on the point on a point on that, or that point of the elliptical orbit. So, this is the physical significance of this particular result. Please keep that picture in mind, because this is sometime very useful in understanding certain phenomena. Okay. So, we have discussed, oops, sorry, I need this, sorry. This is r min is equal to 1 minus epsilon, r, or rather r max is equal to 1 by 1 minus epsilon, and r min is equal to L by 1 plus epsilon. Now, let us forget about this for a moment, and we have derived the velocity expression for two types of orbit in inverse square force field. One is elliptical orbit, which is where the velocity is given by this relation, and one is the parabolic orbit, which we did previously. Now, for both the orbits, we have seen that there are extreme points, the points which is closest to the force center, or the closest approach of the mass which is moving, or the point mass which is moving on this particular orbit. It can come to a shortest distance from the force center, and it can go to another longest possible distance from the force center. Now, these two points where the distance between the force center and the mass is either shortest or longest has certain names. They are called the apices or apicidal points. Okay. For example, this r mean and r max, they are two apicidal points on an elliptical path, right. Now, this apicidal point has certain properties that we need to keep in mind. Apicidal points are points which are 1, points of either maximum or minimum approach. Okay. That is one definition. Second definition is, these are, as you see, this orbit is given as a function of r, I mean r as a function of theta. So, when r goes through a minima or a maxima, we can immediately infer that dr d theta will be equal to 0 in these two extreme points, and that is true in general for any orbit. Now, apicidal point is something which is defined for any central orbit. It is not specific to inverse square force field orbits, but we will be using mostly for inverse square force field. I mean, later on we will be doing calculation based on inverse square force field. So, we are focusing primarily on inverse square force field, but please keep in mind that for any orbit, if the what you call the particle goes through an apicidal points, this relation will be valid. So, dr d theta will be equal to 0. That essentially means dr d theta will be equal to 0, same as du d theta, without surprise, because they are related, u is equal to 1 over r. So, this is another property. Also, not only the spatial derivative, but also the time derivative of r will vanish here, because if you think of it, see, when a particle moves on this particular orbit, let us say, we are just taking this as an example. So, at each point the velocity changes, right, as over time each point the velocity, the value of radial vector changes, and these are extremum points. So, not only the theta, theta derivative of r will vanish, but also the time derivative of r has to vanish, because it is also an extremum point in the space time trajectory, either minimum or maximum point, right. So, r dot will also vanish. Now, what happens is, the way we write our equation for this particular case, the equation is L by r equal to 1 plus epsilon cos theta, but typically we have chosen to write our equation in a particular form, where the reference line is the line where the apices lie. What I am trying to tell you, that if I have, instead of cos theta, theta minus theta 0, that means our axis system is not this, but this, with an angle theta 0 here, right. But we are not doing that. We are assuming, most of the time we are writing equations assuming theta equal to theta 0, and when we do that, we describe this angle theta with respect to a line from which the angle theta is measured. So, anything on that line is theta equal to 0. Now, by simple geometrical consideration, we can understand that the apices or apicidal points has to lie on this particular point, this particular line, okay, because maximum and distance of maximum and minimum approach will take place for either theta equal to 0 or theta equal to pi, or some symmetric position, okay. And so, that symmetry can be achieved if and only if the apices lie on this particular point. So, the third important conclusion is, for apicidal point, theta is equal to 0 or any other angle of symmetry. So, 0, pi, 2 pi, anything, 0 and 2 pi is essentially the same. The third law, again, it is a choice we make by writing this equation in this particular form. This is not a rule, okay. But by using this relation, we can define, or let us assume that for the choice we make, theta is equal to 0 for an apicidal point. Right. Now, oops, once again I removed it, sorry. Now, let us look at this carefully. We have a few relation or few condition for apicidal points. One of the condition is du d theta will vanish. Now, if you go back to the original equation of velocity we wrote, that was du d theta square plus v square is equal to, and this du d theta, sorry, not v square, u square whole multiplied by L square by m square equal to v square. Now, for when we hit during the path or during the trajectory when the particle hits an apicidal point, this term vanishes. So, at a particular point, if we write an apicidal distance by r a, then we immediately see from this relation that L square by r a square m square is equal to v square. Once again, we can take the root of this particular equation and we can write a relation which is v equal to, or r a v equal to L by m. So, this is a very crucial relation we have in hand, right. So, okay. So, how are we going to use this relation? Let's understand this. Now, R A is either a minima or a maxima in the orbit. So, that means the v velocity is either a velocity maxima or minima, because r and v they are inversely related. So, if we write the velocity at the maximum point as v max, okay, corresponding to r mean, and v mean corresponding to r max, then we immediately see from this relation that r max by r mean will be equal to what it will be? It will be v mean by v max, right. So, this is relation, one relation we have. Now, here for this particular case, I removed it again, this is something I have to work on. Okay. So, for an elliptical orbit, r max and r mean are given by this expression. If we put this into this equation, we get r max. So, it will be 1 plus epsilon by 1 minus epsilon equal to v mean by v max. Now, I do not need it anymore, right. Now, if you start adding and subtracting the numerator and denominator, or basically you have to first do the subtraction. So, we immediately see that epsilon equal to v. So, r max is equal to L by 1 minus epsilon, right. This is max. So, this will stay here, v min, yeah, looks good, right. So, if we perform this, we see that it will be v max minus v min divided by v max plus v min. And please remember that this is specially for the elliptical orbit, it is not a general relation. This relation is a general relation, but this one is not. Now, this relation is extremely useful, because in an elliptical orbit, if we know, so that means if we know the speed at the apicidal points, by the way, this, if this is my elliptical orbit, this is my apicidal line, this is the r mean, and there are specific names for it, especially for an elliptical orbit. Okay. So, the names are, this one is called apogee and this one is called perigee. So, we have a name for it. This is called apogee and this is called perigee. This is the force center. So, minimum distance is this, maximum distance is that. So, if we only know the velocities at these 2 points, for example, let us say we are talking about an artificial satellite. If we know the velocity, and this is my earth, okay. So, let us say we have this is my earth, almost a sphere, which is not true, and this is the closest approach to earth and this is the furthest approach to earth of this particular satellite, and we know the velocities at this position and velocity at this position, assuming that it is going in this direction. So, using this relation we can immediately find out what is the eccentricity of the orbit, right. So, also we see that as V max if V max is equal to V min, then what happens? Then this term vanishes and we have an uniform epsilon equal to 0, and that essentially means there is an uniform velocity, and that exactly what happens in a circular orbit. A circular orbit is there is only one velocity possible. Okay. If it is under central force, we will see that later in more details, that there is only one velocity possible and it comes with an eccentricity of 0. Okay. So, this is how it is, and also the parabola we draw previously, the velocity was some constant times 1 plus cos theta. Okay. So, one of the apis, the apogee distance is this and the perigee distance was at infinity. Now, for a parabolic orbit in inverse square force field, velocity at infinity essentially means that it is I mean the particle has gone to infinity with 0 energy, because at infinity the effect of attractive force is also 0, and that essentially means that the escape velocity path possible, the lowest energy possible escape velocity path with lowest energy is a parabolic orbit with 0 total energy on it. We will discuss all this little bit more details later, but for now we will stop here, and in the next class we will start doing some problems on this. Thank you.